Welcome to another lecture on rational functions. We know that rational functions can be analyzed using key features such as asymptotes, intercepts, slope that is positive or negative, increasing or decreasing, or the domain set and range set, and the positive and the negative intervals. So here we are starting with a very simple rational function known as a homographic function. That's another name for a rational function whose numerator and denominator are both linear functions. And we know that the root of the denominator here is x equals -1/2, and that will be playing the role of the vertical asymptote, which is shown with the dashed lines as you see. And the ratio of the leading coefficients in the top and bottom is 4/2, which is 2. So y equals 2 would be the horizontal asymptote, the equation of horizontal asymptote for this rational function. So that's how the graph looks like. It is also called an equilateral or rectangular hyperbola. That's another name of this graph. These are like famous rational functions where the numerator and denominator are both linear functions, and they have like different names. So that's the situation, and the behavior at a neighborhood of the vertical asymptote is similar to that of the reciprocal of linear functions that has been discussed in the past. As you see, the graph is approaching its horizontal asymptote on the left-hand side when x approaches -infinity, and on the right-hand side when x approaches +infinity, y approaches 2 from below, as you see here. So discussing other types of rational functions with different types of asymptotes, let's have a look at this other one. So this one has a quadratic numerator. So we have x squared minus 4x plus 1. That's a quadratic numerator, but the denominator is just x plus 1, which is linear. So the degree of the top is 1 more than the degree of the bottom. Therefore, we must have a slant asymptote, or another name is oblique asymptote. The denominator is, of course, if you set the denominator equal to 0, it's going to give us x equals -1 as the equation of the vertical asymptote. And we're going to see how the graph would look like. So we have this vertical asymptote x equals -1, and the slant asymptote, which is shown by this green dashed line, whose equation is y equals x minus 5. So you see how the graph looks like. This is the graph of the function y equals x squared minus 4x plus 5 over x plus 1. So we have one slant asymptote and one vertical asymptote, but we do not have any horizontal asymptote. We have mentioned in the past that whenever there is a slant asymptote, then there is no horizontal asymptote. They don't go together. Okay, so we discussed a case where the top polynomial was linear, the bottom was also linear, and now we discussed another one where the top was quadratic, bottom was linear. We are going to continue our journey, and this time we're going to have a linear polynomial on the top and a quadratic in the bottom instead. Now this denominator, if you look at it, x squared plus 1, is a quadratic expression which has no real roots actually. So if you set x squared plus 1 equal to 0 with the intention of finding any equations for the vertical asymptote, you will see that the equation will have no real roots. This means that the denominator is never ever equal to 0, and that means that x squared plus 1 is an always positive expression. And when something is always positive, regardless of value of x, it will never be equal to 0. Therefore, we do not have a vertical asymptote. So this is one example of a rational function that does not actually have a vertical asymptote. We never said that all the rational functions in the world must have a vertical asymptote. So as you see, we don't have any vertical asymptote, but because the degree of the top is less than the degree of the bottom, we do have a horizontal asymptote whose equation is y equals 0. That is the x-axis. So you see that here, the x-axis plays the role of the horizontal asymptote, and as x approaches positive or negative infinity, then y approaches 0, either from above on the right hand side or from below on the left hand side. So this is just another example. No vertical asymptote. We examine another one. This one, the top is 1, the bottom is quadratic. So this is a reciprocal of a quadratic function with actually 2 zeros, and 1 0 is x equals 3, 1 is negative 3, and those are playing the role of the vertical asymptotes. So here we have actually 2 vertical asymptotes that are the roots of the denominator, and this is how the graph looks like. Generally speaking, reciprocal of quadratic functions with 2 zeros have 3 parts, with the middle one reaching a maximum, like in this case, or minimum point. So one part is on the left, one part is on the right, and the middle part, as you see, it is reaching a maximum point here. Sometimes it could be a minimum point. This point is equidistant from the 2 vertical asymptotes. So that's the nature of reciprocal of quadratic functions. That's how it looks like. Again, horizontal asymptote is y equals 0, or the x-axis, but the vertical asymptotes are x equals 3 and x equals negative 3. Let's have a look at another rational function. The top is linear, bottom is quadratic. So let's see how this one looks like. So this time it's not reciprocal. We can't say this is reciprocal of a quadratic function, but the top is linear. It's not a constant, and the bottom is quadratic. And now we see that the roots of the denominator are actually 4 and negative 3. So x equals 4 and x equals negative 3 would be playing the role of a vertical asymptote for this function. As you clearly see, again, we have 3 parts. One is on the left, one is in the middle, and one is on the right-hand side. That's how the graph looks like. Horizontal asymptote, once again, it's y equals 0. That is the x-axis. We don't have slant asymptote, obviously, because the degree of the top is not one more than the other bottom. And if we examine another one, here it says 2 over x squared minus 4. This one, again, the top is a constant. So it's a variation of reciprocal of quadratic function. The denominator has 2 roots, and the roots are 2 and negative 2. Therefore, x equals 2 and x equals negative 2. If I can find it somewhere, those are the, yes, it's right here. Those are the vertical asymptotes for this function. Again, you see, because this is reciprocal of a quadratic function, we do have a middle part, and this middle part has a little section that reaches a maximum point, and this point is equidistant from the 2 vertical asymptotes as mentioned before. And if instead of 1 we have 2 in the numerator, that just represents a vertical stretch by factor of 2, so that's not a big deal. We could have had 1, but 2 is also okay. So that's how the graph looks like. And finally, this one is x plus 1 over x squared minus 9. So this is another variation. We have 2 vertical asymptotes, x equals 3 and x equals negative 3. Okay, so everything is clear, but this time the middle part does not have a minimum or maximum point. In fact, we do have some sort of inflection point, and the behavior near asymptotes is similar to that of reciprocals of linear functions, in the same way that we have determined the behavior at the neighborhood of the vertical asymptotes in the past. We just follow the same procedure. And what else can we say about this function? Well, the x-axis plays the role of the horizontal asymptote. Then this is another one. This time the degree of the numerator is 3. We have a cubic polynomial at the top, and we have a linear binomial in the denominator, whose root is actually x equals 5. So that is a vertical asymptote for this function, but we don't have a slant asymptote this time. You see how the graph looks like. We don't have a slant asymptote because the degree of the top is 2 more than the degree of the bottom. The top is a cubic polynomial of degree 3. The bottom is a linear polynomial with degree 1. So if the top was 3, bottom was 2, we would have a slant or oblique asymptote. Or if the top was 2, bottom was 1, degree 1, then again we would have an oblique asymptote. But right now, the top is 3, bottom is 1. So we don't have slant asymptote. We don't even have a horizontal asymptote because the degree of the top is more than the degree of the bottom. And the only asymptote we have for this kind of function is only the vertical asymptote, whose equation is x equals 5. And that is determined by setting the denominator equal to 0, as you very well know. So it's very interesting how different these graphs of rational functions are with multiple situations. Sometimes we have one vertical asymptote, sometimes 2, sometimes 3, sometimes even no vertical asymptotes. Sometimes we do have oblique asymptotes, sometimes we don't. So you see that there's all sorts of possibilities out there for all these functions. So let me just, out of curiosity or perhaps for fun, I just turn everything on and let's see what happens. All these examples, one on top of the other, it shows all the possibilities. This is the advantage of using technology, of course. So all the asymptotes are shown with dashed lines and everything else with solid lines. So that's a whole bunch of graphs of rational functions. Okay, so please keep practicing, and thank you very much for